Okay, let's start today's discussion. So we're going to enter into Chapter 5. So Chapter 5, we're going to start really dig into the analysis of circuit, especially amplified circuits. So we're going to move away from the understanding of bipolar junction, the physics of bipolar junction transistor, through the understanding of basic device model, device equations, current voltage equations, and small signal models. We're going to enter into analysis of how do you, based on these understanding of model of transistors, how do we actually use these transistors and construct circuit architectures. So in Chapter 5, we're going to touch basically, I'm going to start with general consideration in terms of understanding what is the basics of a amplifier. How does one consider what are the key factors you wish to evaluate or you wish to analyze in understanding an amplifier circuit? So we're going to talk about general consideration of amplifying circuits. And the next thing is, of course, as I said, if you're dealing with analog signals, what happened is that you wanted to, these signals are typically small. Therefore, these are a small signal. You start at a particular point. So biasing point is a very important thing. So as I said, once when we want to start with generating a small signal model, you start with understanding where your standing point is. That's called the operating point. So some of the example is that you typically have the operating point is given to you. For example, I'm telling you the biasing current of the circuit is at a particular point. But in a lot of the design, one of the key challenge for designer is to place your circuit at this particular operating point. That's called the biasing design or biasing circuits. So how does one make sure that as I said, I use this analogy that it's like if I'm a performer, I wanted to stand at the spotlight. How does one make sure that every time I will be able to stand at this particular point, stable and reliable? So that's called biasing design. What type of design to ensure your performance right at this particular point? That's called biasing design. So we're going to talk about various ways of doing that and what are the trade-offs. So as I said, design, I will talk about what are the performance or figure merits, but one of the key important things is stability, meaning that every time, if you're performing 10 times in a stage, you want to make sure that 10 times you're right at the spotlight, does not miss any time. That's called the stability or robustness. We're going to talk about that when we talk about biasing design, of course. And then after setting after providing the particular schemes that we can use to setting your circuit at a particular point, we're going to talk about, of course, amplifier topology, various ways of constructing the amplifier. These are the three important ways. One is called C stands for comma. So CE is common what? Common what? You have only 3 terminals, so common emitter. Yes, this is common emitter. So by the same method, this is common base and common collector. Okay, so common typically means that those are the reference points. So if you look at the circuit architecture on the right, if I'm setting it to ground, it's typically a common to AC signal or DC biasing. So these are DC biasing. So if I'm setting my emitter to ground, this is a very typical common emitter architecture. If I'm setting my base to a DC level, the 2 terminal which left uncommon, I should say, will then be left as the input and output. So you can see that input so for common, it's a big one. I think it's a Hornet. afraid of the hornet. Anyway, let's make sure. 所以那个窗户打开，看他会出去好不好？不要抓他啦！不要抓他啦！ It's gonna。等一下被那个被咬怎么办？它是一个风哎。I'm gonna okay. Okay, never mind. I don't. Okay, anyway, so you sure you want to take this class? Okay. So anyway, we'll go back to our architecture. One of the key points is that the common node is a reference node, and then you have two input and output. There's in an amplifier, you definitely have an input and output. Therefore, the input will then be mostly at base, that's common emitter, and then your output collector is the typical output. So that's what we call the common emitter architecture. And then you have this common base. You can have the base as the reference node, and we have input coming in from emitter, output at collector. And of course, the last one is that we could have our collector being at a DC level, a bias at DC level, and then your input is coming in from base and then going out at the emitter. That's called the common collector. Okay? So these are the structures that we're basically going to follow, and we're going to talk about what are the features. They have different features. These are, why are we using these combination of architectures to construct a favorable performance for the amplifier? So typically for example, if you remember in our first class, I introduced a classic design, right? The classic operational amplifier. It has all these three components. You want to use these components in order to construct to meet the various requirements at each stage, and so you have multiple stages to construct a perfect or more ideal characteristic of your amplifying circuit. So before we're actually moving to the details, so we're basically going to start talking about what is an analog circuit. A typical analog circuit is typically a circuit which processes signals, analog signals. So when you process the signal, these signals are typically, in most cases, are voltages. You transform it into voltage at the very beginning. For example, if I'm sensing my signal, as I use the example of a pistol circuit, for example, for your image sensor, you have pistol circuit. You convert the signal, the light signal, into voltage at the very beginning. And then you transduce into processing stages and then transform into output. So what we're actually doing in most of the analog circuit is to process these voltage signals. So these are the main part. Of course, you can deal with current signals, but that's fairly rare. So mostly we're dealing with voltage signals. So we're going to talk about mostly our voltage amplifier, meaning that there's various type of amplifier. If you take circuit theory, what are the other types? There's voltage amplifier. You can do current amplifier. You can have transconductance amplifiers or resistance amplifier, depending on your input and output signal. But if my input and output signal are both voltages, and that would be a best solution would then to use a voltage amplifier. So in a voltage amplifier, what are one of the key things people look for are the performance factors. So if I give you a voltage amplifier, how does one evaluate whether this is a good voltage amplifier or a bad voltage amplifier? How does one evaluate? So there are, we call the performance factors. What are the key performance factors a designer or a user will look for? So typically what you refer to, or in a lot of the circuit, if you ever go into circuit design studies, you look at the paper, they have the figure merit tables. So those are, you can either refer that as a figure of merit in a circuit evaluation. So performance factors sometimes referred to as figure of merits. So what are the key figure of merits? What are the things they're looking for in evaluating a circuit, whether it's good or bad? one of the key important thing is because it's a voltage amplifier, of course, you look for amplification, the gain. How much does it provide, the gain of this amplifier? Next thing, of course, is speed. You want to make sure that it follows when I apply a certain amount of signals. But this part we're not going to talk about until, I think, chapter 11, when we talk about frequency response. So when we refer to, this will be addressed when we talk about frequency response. So how wide can this circuit be? Okay? And then the next thing is, of course, the power. How much, what is your cost in operating the circuit? That's the power. In this circuit, it will depend on, in most of the analog circuit, for digital circuit, there's we'll call the transition or transient power. But in analog circuit, mostly there's a DC power. So DC power is power, this is dissipation, DIS. Dissipated power is the current that is being biasing the circuit and VCC. So this will depend a lot on how the biasing circuit is designed. So we're going to talk about that a little bit. It will be related to the biasing design. So how much does it put in order for your circuit to be stay at this particular state, waiting for the signal to come in? That's called the DC power or biasing power. Typically, biasing power will determine most of the power in an analog circuit. And of course, lastly, we'll talk about whether it's a low noise design or whether it's being disturbed by noise signal. So this part, we're going to a little bit, there of course, if you go into analog circuit design, there's a lot of factors that allow us to design or analyze, such as numbers like noise figures or detailed noise analysis. But in this case, we're simply going to talk about, in this class, we're simply going to address some methods in reducing the noise in the system, especially in differential pair. This is also in, I think, in chapter 12, or I don't know, maybe later in the discussion. Okay? So any questions on this part? It's not leaving. I don't want to go. Okay, so what we're going to do is I'm going to jump over to that form. This looks alive. So what we're going to do is talk about, okay, as I said, aside from having a gain, how does one evaluate whether a voltage amplifier is a good amplifier? So one of the key important things is, other than this voltage gain, you wanted to make sure that your amplifier actually deal with interface with signal very well. That's when we introduce something called, you see the green part where there's input impedance and output Z in, Z out. So we're going to talk about impedance. Impedance is the, I'm just going to give you the definition, the ratio of a voltage phasor to current phasor. So this is, in circuit theory, you already deal with that. So I'm just going to define it. So by definition, the impedance will be V as a function of frequency, current as a function of frequency. So this will be your impedance. There will be the real part and imaginary part. Typically, the real part will be the resistive part, and the X part, the imaginary part, is typically capacitance or inductance. But in this case, in our the circuit that we're going to discuss is mostly capacitive component. So this is resistive component introduced by the resistive. And this is capacitive. If we're staying in relatively low frequency domain. So in analyze and amplify it aside from just the pure voltage gain, for example, we also want to look at its interfacing capability, which will then be referred to how does one characterize how well it interacts with signals, input and output signals. Then that's the interfacing point. So the interfacing will then be determined by two of the main characteristics, which is input and output impedance. So the input will determine, these will determine the how well does it transfer of signals between stages. So the point is that I want to, aside from just the main building, I have to interface with previous or next stage. So these stages will then limit the interface quality, or the input and output impedance will then affect how well does the voltage amplifier take in the signal without degrading it right at the interface. So how does one build this interface is very important in this design as well. So that we're going to look at, so think about a voltage amplifier. Let me use a voltage amplifier example. What do you want? So let's say if I have a voltage amplifier. For a voltage amplifier, what we typically do is, let's say, VCC ground. If I'm only looking at the small signal, I could actually construct a two-port model which describe how I will wrap it with a black box. And only looking at these lines, the characteristic of input and output, the corresponding characteristic, and using an equivalent two-port model to describe this. So for a voltage amplifier, we know that it will then have a input impedance. And then, because it's a voltage amplifier, so I'm using a voltage control voltage source. And then output VI. So a general, this is a general, we call it two-port model. Two-port model of a voltage amplifier to describe how does this input and output signal voltage amp. Okay? So this is equivalent to this equivalent two-port model. And let me finish this description. So I have a voltage gain. That's the key voltage AV. I'm just going to talk about that a little bit. So this voltage control voltage source depends on its input voltage here. V is in V1. Okay? So if this is the case, this is my voltage control voltage is the same thing. So if this is my voltage control voltage source, what do I look for? What do I look for in input and output impedance? Does anyone know? What do I want? For an ideal, does anyone know if it's an ideal? For an ideal, an ideal voltage source, a voltage amplifier, I should say. What do I look for in input, output? And of course, ideally, you want to have infinite, as high as possible. You want, these are the three important parameters. Let me write it down. So three important parameters. Vin is the input impedance. Zout is the output impedance. And of course, AVO is typically referred to as the open circuit. The O stands for open circuit voltage gain. This is when you're not connecting to a load. That's how, what is the amount of voltage gain when this is open circuit. Okay? So let's give you a general problem. So if this is my amplifier, when you use it, you typically connect it to a source signal coming from a transducer, a sensor, for example. So whatever you have at the beginning, here, at the source side, it will look something more like this. So in general, I have all kinds of sources, input sources. So input sources, a typical model for your input signal source will be something more like this. If it's a voltage source, it will look something more like this. Okay? And at my output terminal, once your amplifier is being done, for example, if my signal is already being amplified through this wireless system transmitted into the speaker, I need to drive the speaker. So the speaker has we call the loading resistance. So your output typically is referred to, the output terminal is typically referred to as a loading resistor. So you can model it as a load. So our load is called a loading resistor. Let me write it down here. So there's two things depending on your signal, where your signal coming in, and this is where the output is being delivered out. So this is called a loading resistor. And then RS is the source resistor. So these are typical models for your input and outputs. You need to take in the signal, and then this may be my microphone. Microphone can be modeled as a part that taking in signal, and then there may be a parasitic source resistance, parasitic series resistance. And here is the loading resistance. So if I look at my final output, if I actually construct this circuit, this is my V out. So I want to know the overall V out versus V in. V out versus Vs. That's my source signal. Will then become Rs plus Rin by Z. I'm using impedance. So if you construct the output and input relationship, it will be something like this. R load, R out. Okay? So this is your final relationship between the output and input sources, right? If this is the case, if I want to get the most obtainable results, maximum gain, which is AVO, how do I get this? I want to how do I approach more ideal results? I want input resistance to be what? What do I want? I want it larger or small? Just give me direction. Input resistance, large. I want it large so I don't see this, right? So if V approaches infinite, this term will then approach 1. You want to approach 1. And then I want output resistance. This is what I can control. Remember, RS and R load is your customer. You cannot control it. It's your input. It's whatever. You want any customer to be satisfied, right? So loading is your customer. Sources is whatever you need to fit in. You need to fit to your customer. Your designer, you can only manipulate these two. These are the external environment. You want to make sure that your circuit is robust. In any type of environment, it should deliver AVO. If you can design that, that will be perfect. It will be independent of what kind of sources you're dealing with or what kind of loading you're dealing with. So for an ideal voltage amplifier or for example, operational amplifiers. Target is to have input impedance approaching infinite. And I want my output impedance. Sorry, I made a mistake. I want my Z also. I forgot to do this. Let me change the color. So this is the one that I can control. The white one are the ones that's within my design. And the rest is the environment. You want to make sure that at whatever environment, you will be able to get the maximum performance, right? So the yellow one is external. These are internal. Internal is what you can design. You want to design an amplifier which fit all conditions, right? So then what do I want for ZL? Yes, at small pulse, I want to approach 0 for ideal. Right? So remember this. This is what we're going to look for if we're dealing with a voltage amplifier. So how does one make sure that this input impedance as high as possible, output, it's gone. Yes. Okay, I can move to the center. Finally. Okay, so then we have a basic understanding as to what is needed for a voltage amplifier. The next thing is then, how does one determine its impedance in a circuit? So these are all small signal models. So these are, we want to find the small signal. So how does one find the small signal impedance in a circuit? If I give you an arbitrary circuit, arbitrary amplifier, how does one find these impedance? So the idea is, first of all, for a circuit, whatever model you have, you want to make sure that if this is my circuit, if I'm looking into the input terminal, since we're not actually dealing with capacitive component, I'm going to limit this discussion to input resistance for this class. For at least for this chapter, we're going to limit ourselves on only talking about resistance because capacitive components are not yet being considered. So what we're going to do is to find Rin, Rl. So how do we find the input and output resistance? The way to do this is that I'm setting and make sure that my output is open. I'm opening my output. And then what is typically being done is that if I don't know what my input resistance is, typically what one can do is to give a test voltage and look at its test current. I'm going to use this scheme a lot in our future analysis. For example, if you have a common emitter circuit, you want to look at what your input resistance is, then we're going to construct our small signal model and then do this. So the input resistance will be defined, Rin. The resistance looking in, Rin, is by definition Vx. The relationship between my test voltage and test current. This is also true if you have a real circuit. If you have a real circuit, what you do is that you open the output and then look into the voltage and current relationship when you're looking into the input terminal. So that's how one gets its input. So in this analysis, you want to set all. First, you set all independent sources to ground, to 0. That means open V to 0, which means it's open. I to 0, I to 0 means open, B to 0 means short. So you short all, let me highlight, independent. If there's any independent sources inside this circuit, you set it to 0. And before we finding these input and output resistance. Well, those go through a lot of examples. And then for output terminal, if you're looking at the output terminal, the same thing, you give a test voltage, Vx, and look at its test current. But in this case, we want to set our sources to 0. So you short input. So in this case, short input. That means that you set your independent sources to 0. Vs. We set our independent sources to 0 and look at what is the corresponding or equivalent voltage and current relationship. So that would then give us R out. So the R out will be defined as Vx, Ix as well during this test condition. So you test the front to get the input resistance, test the back for the output resistance. Once you have this, then we can construct our overall small signal model, two-pole model. You have the input resistance, output resistance, voltage gain. So in the following discussion, most of the questions we're going to ask you is that once you design your amplifier, these are the 3 key parameters you need to deliver for a voltage amplifier. At least in chapter 5, you need to deliver 3 key parameters: AVO, how much voltage gain, input, output. So that will give us how well it amplifies the signal and how well it interacts with input and output terminals, input and output signals. So this is for interfacing. And this is internally how well does amplifier deliver its amplification factor. Okay? So once we have this, then any of the circuit, whatever it is, for example, if I have a common emitter amplifier, for example, looking like this, I'm just giving a very rough. I can wrap it up and then say that it's equivalent to R in So what we're going to do in this class is that I'm going to give you various type of architecture and various type of circuit architecture or modification of, for example, common emitter stages. Then you have to turn it into this two-pole model, finding out these 3 key parameters. Once this has been constructed, then we can actually put it into a stage of your amplifier and then interact with other stages and then construct a larger block or larger circuit architecture. Okay, so you have the unit block. This is the same thing. You build a equivalent model. Once this is being done, you can then use this model to interact with various stages. So this is a next level of abstraction, is that you build this model, and then this can be used when we have multiple stages in your amplifier. So what we're going to do for this lecture, or at least for this week, is from this to this. How does one translate these two? And how does one finding this input and output resistance behavior? And of course, voltage gain. Okay, good. So that's the main target of this circuit. So before we actually go into these various architecture, for example, the common emitter, we're going to start with common emitter and common base and common collector, of course. But before we actually go into these different stages, introducing different stages, we want to talk about the next important thing is called setting up your amplifier to the correct position, which is called setting the operating. Before you can start watching or see the performance of the singer, you want to make sure that your singer is standing at the spotlight, as I said. So how does one determine its operating point? Is by, as we already know, you do some large signal analysis. So what is typically being done is that before I decide where I wanted to stand, the first thing we do is to survey the whole stage. So for example, I'm just going to give a very rough analysis. So before you come into the stage, I want to see where should I stand to get the best performance. That's called selecting the operating point. So selecting, how does one select an operating point? So typically being done is that you want to construct something called a transfer function. So this will be then be my V in. This will be a large signal range, V in and V out. So you do a survey across the whole stage. I start from this end. For example, I start from 0 to VCC mostly. So this will be my V in. So this will be fairly simple. What would typically being done is that if I want to measure it, simply I'm ramping this. I'm just going to give it a ramp of voltage and then look at what is corresponding voltage. A voltmeter to measure the output voltage, the corresponding output signal. So what do you think it will look like? Does anyone want to try? So if I'm starting at 0, where do you think, anytime when you do this type of, we're not going to do a detail. I'm just going to give you a rough transfer function description. So when you do this type of transfer function analysis, one of the key things is that you find points. You find key points. Or, for example, you look at 0. What do you expect this device will be? The output. When this is 0, your output will be what? What do you think? Anyone want to guess? What do you think your output will be? At 0, just to 0. So this is V out. Transfer function is V in, V out, right? So where do you think your V out at 0 will be? V what? VBE, oh yeah, I can give you a VBE. I can use, for this transistor, I'm going to give you a parameter because we can give it parameters. So let's say this is Q1, and it has, for example, Q1 has a VBE on of 0.8, and then you have a beta of like 100. So just a rough parameter, right? So what do you think it will look like for this point? At 0, this transistor will be on or will be off, right? So it will stay off before 0.8. So you're expecting the collector current, because Q1 is off. So at this, between 0 to 0.8, Q1 is off, meaning that IC equals to what? You already forgot? Equals to 0. Yes, correct. Therefore, my output, let me write down. Yes, correct. My output by DC is VCC, ICRC. So since I see 0, I should have a 0. I should stay at, let me use a different color. So in between, because this transistor is off, so Q1 is off, I should stay at VCC, right? Once it turns on, because this is a exponential model, so it doesn't really matter. You would then have a drastic drop. I'm not going to go into how much gain there is. But basically, roughly, if you look at this, the transfer characteristic, it will be something like this. It will be very quickly because it's an exponential voltage. So you would then have a very small range of increase of voltage. If you use the constant voltage model, it will be a straight line. But in real case, it will be somewhat very high gain because exponential dependency. Therefore, you see a significant drop, and then it will stop at where? Where do you think the third turning point will be? So at this range, at this very sharp turn, I have 3 ranges. I have, as I said, in this part, this is 1, and then I have 2, region 2. This is when you have a sharp transition. This is when transistors are on, this is on, the voltage is high. So that Q1 is in active, right? Because my collector voltage is high. But once it drops until where? Until very low. So until when? Until, what is the turning point? What do you think this turning point be? About, so I forgot to give another parameters. So VCE set using VCE of 0.4 volt. So meaning that if it drops until VCE set, this is 0.4. This is VCE set. When it drops to lower than VCE set, it would then enter saturation. And then the collector current will then does not correspond to VBE that much, so will then flatten out. So there's basically 3 regions: 1 when it's off, 2 when it's inactive, and then 3 is saturation. Q1. Okay, so one of the key important things in large signal analysis is that first you survey the whole stage and look for where do you want your operating point be? 1, 2, or 3? Which region? Where do you want it? 2, of course. We wanted to make sure that our amplifier, our transistor is in active mode in order for the amplification or transconductance to be active. The small signal model will be valid when it's only in 2. And where do you think I should pick? There's a various region for 2. Where do you think I should stand? Yes, at the middle, that's correct. So in most cases, in most of the design, you want to make sure that if I already draw this plot, then I would decide that I should stand, let me get over. So I find this is the maximum. This is typically V out max, right? This is V out minimum. If I'm considering region 2. So typically what I want to do is to place operating point at the center. Max plus VL minimum. The reason why typically what we want to do, it's not necessarily every time, but in typical design, you want to stand in the center because I don't want to fall. Because you want to make sure that when you have a signal, you will then allow the maximum swing. We call the maximum swing. You will allow you to dance. This is your output. That's your maximum swing. You want to make sure that you have the maximum swing. If you place it in the middle, then I should then have a maximum margins for me to dance. Otherwise, I will be limited. If I stand right at the stage, at this end, it'll probably fall down the stage. That means there will be distortion on your signal. So in typical cases, you want to stand in the So before I start going through various biasing design, I'm just going to tell you that in an integrated circuit, none of this will be used if you're using integrated circuit. So the real biasing scheme is, if you're using integrated architecture, is typically will be introduced. Yes, 谢谢，谁帮我擦一下？就是 what we're going to do. Yes. Thank you. So what we're going to do next is just to discuss how do you set the biasing to place your circuit at a particular operating point through what we call the biasing circuit. So these are most likely like if you're doing discrete circuit design. If you're doing integrated circuit design, one of the most important solution is the architecture we're not going to talk yet. So this is mostly for discrete circuits, meaning that if you buy a transistors and you go get these resistors component. But in most integrated circuit, I want to emphasize again, you don't actually have too much room for placing resistors. Resistors are very costly and unreliable component. So typically in real circuits, you don't actually use these schemes. But we're still going to talk about the schemes, so for you to get an understanding as to what are the key points people are looking for in the biasing design. So what are the features? But I'm just going to tell you that these are old-fashioned solutions, which will not be used in integrated designs. So we're going to introduce a few of the biasing scheme and going to discuss what are the pros and cons of these circuits. So for bipolar circuits, our biasing circuit for, let me just emphasize, this is for discrete BJT circuits, meaning that you go get the transistor as a discrete component rather than having that in an integrated circuit. So for example, so we're going to introduce one is called, referred to as the simple bias scheme. This is the most simple one, simple bias scheme. So if you think about it, bipolar junction transistor, one of the key things is that you could actually set your biasing. Typically what we wanted to do is to set, rather than setting VB, typically what we want to set is IC. To set ICQ, because ICQ is actually more related to your small signal